Welcome to your quick lesson on radiometric dating. You have this Google Doc that I'm sharing with you. There is the first page, which is some brief review, hopefully, about atomic structure and atomic traits that you might have seen in a class before. This is a good video that might help you with review if you need it. And what I'm going to do is talk to you today about isotopes, radioactive decay, and radiometric dating via this slideshow, which I'm also going to be sharing with you. And hopefully this will give you a brief introduction into radiometric dating, which will allow us to do a lab on Thursday and Friday. Now, there are some big complications with how we date things from the formation of the Earth all the way to the arrival of hominids a couple 100,000 years ago. The first is that destructive forces constantly change the exterior of the surface. Multiple times, Earth has been bombarded by large asteroids. We've had plate tectonic movements where continents go under the ocean subducting, which leads to the rocks being dissolved. Earthquakes, volcanoes, ice sheets that cover the entire surface of the Earth, such as snowball Earth. We've had a lot of forces that constantly destroy evidence on the surface of the Earth. But we also have constructive forces. Right now, the Himalayas are growing a couple centimeters every year, and the same is true for the Andes Mountains, and we have other constructive forces that will cause new mountain ranges to arise and new continents to be created as well. And land masses slowly shift on the surface as well. So Vermont used to be in a location where the Bahamas are, and we had a shallow surface ocean, which means that the climate and the environment that shaped the rocks and the evidence in those rocks changes with those different climates. And the biggest problem is that most evidence, which is living organisms, plants, animals, bacteria, often decay in a few years if they're exposed to oxygen and if they're not enclosed in some sort of sediment or mud. Which brings us to a problem with when we see geologic features such as this shale and limestone waterfall near Ithaca, Vermont. How do we know that it's 380 million years old? And how do we know that it was formed in this large underwater Acadian mountain range that formed about 380 million years ago, that stretched all the way from Maine down to North Carolina, which now forms the Appalachian Mountains? How do we know that there was an ocean here? How do we know there was a mountain range that formed 380 million years ago? The answer is radiometric dating. Now, to help you start thinking about radiometric dating, I'm going to have you watch this video, which is going to talk about things related to daughter isotopes, radioactive isotopes, and how isotopes are quote-unquote sealed in different types of rocks and how that helps us with evidence towards understanding the age of different things. So the first thing we have to know is isotopes. Isotopes are different variations, different flavors, so to speak, of atoms in which there's variations in the number of neutrons in the nucleus. Now, the nucleus of the atom, as best I can explain to you, is like the VIP club, or it's a super cool place to hang out. Why is it so cool? Why is it so exclusive? We don't want to have too many people in there. Suddenly, if everyone is in there, it doesn't become so exclusive. So part of the reason why the VIP club is so exclusive is that we have a bunch of protons, positively charged molecules, that don't like each other. But because there's this force that we call the strong force in atoms' nuclei, they're able to sort of commingle. But if you put too many people in the VIP club, suddenly those protons get a little bit angry, get a little agitated, they don't feel so special anymore, and that leads to some isotopes that have extra neutrons to become radioactive and unstable. And they're going to try and drop some of those extra neutrons to make the VIP club a little bit more exclusive. So isotopes are really just these variations of elements that have too many neutrons. The VIP club isn't so exclusive anymore. Here's a good example of carbon-12, which is our non-radioactive version of carbon. We have carbon-13 and carbon-14, which have either 1 or 2 extra neutrons. And the same is true for hydrogen 1, 2, and 3, where we either have 1 or 2 neutrons, while hydrogen in the normal state has no neutrons. So radioactive decay is the process in which the VIP club reasserts itself. It sort of uses the instability of the nucleus, the instability of the VIP club, to bounce, so to speak, get rid of those extra peeps, those extra neutrons that we really don't want in the club, because we want the VIP club to be stable and exclusive. So radioactive decay is the ability for the nucleus to shoot out charged particles, often some series of protons and neutrons, in order to achieve that stable isotope. So the parent isotope is going to be the radioactive unstable VIP club. It's going to get rid of those peeps that we really don't want in there. And as the result, the daughter nuclei is going to become a stable isotope. It's not going to be radioactive. And it's going to likely have a few less protons and neutrons. Now, the important thing is that the frequency of this discharge, this event, is very consistent for a specific isotope. It might be every year, it might be every 10,000 years, it might be every 100 million years. There's a very known constant discharge for every specific type of isotope if you're looking at a lot of, for example, uranium atoms in a given piece of material. The frequency at which one given uranium atom will get rid of its extra peeps is a very constant value, which gives us some good information to think about aging different materials. So that brings us to radiometric dating and half-lives. Now, a half-life is the certain time that it takes for 50% of an unstable isotope to become the stable isotope. As you have probably figured out with our sugar crystal labs, there are millions and billions of singular molecules and atoms, and even small things like sugar crystals. So when we look at the initial radioactive material in maybe a rock or a fossil or some sort of thing that we're trying to date, there's billions, if not trillions, of radioactive atoms in that material. And the half-life of that material is going to be how long it takes for half of that radioactive material, all of those billions of atoms, to kick out those extra neutrons, reassert the VIP club, and become stable. And then another half-life will happen where half of the remaining radioactive material will become stable again, and so on and so forth. So each half-life, we are decreasing the material of radioactive material by half, so 100, 50, 25, while we're also increasing the amount of stable isotopes by half as well. So we'll go from 0 to 50, 50 to 75, 75 to 87.5. By measuring the change in nuclear isotopes over time, or looking at that ratio between stable and unstable, we can have a really good idea as to how old an object is. The tricky thing becomes different isotopes have different half-lives. So if there's too little of a certain type of an isotope, it might mean that it becomes harder and harder to measure. So we have to be specific with what types of isotopes we use, and what does that mean for our ability to measure the age of materials. Now, there are 4 questions I want you to try and answer as best you can. The first 2 are about the information I just presented. The other 2 have to do with carbon-14, which is a radioactive isotope that we use to measure biological material. It has a half-life of 5,730 years. So the first question is going to be asking how much material I have after 22,920 years. The second one is going to be asking you about if I have 20 grams of carbon-14 in a 100-gram tooth, how many years will pass until there's 1 gram of carbon-14 left? The half-life can be multiplied or divided into time periods to give you the number of half-lives that have occurred. I hope you guys have a great day. You're also finishing your rock labs for tomorrow. I have office hours, so if you need help, come see me. Have a great day. See you soon.